Another way to assess the fit of the least squares regression model is to look at the coefficient of determination. So we know that the correlation coefficient is denoted with R. If we take that value R and we square it, we end up with R squared, or also known as the coefficient of determination. So what that value is it describes the proportion of variability of the dependent variable y accounted for or explained by the independent variable x. So if we take a scatter plot and we look at this, grab some points here, and let's suppose this is our least squares regression line, and we have our x and our y. As we move along the line, we have variability in y, so the y hats will change as x changes. So that variability is the variability that is explained by the least squares regression line, and we use the sum of the squares of the regression to describe it. There's also another source of variability that we did previously, the sum of the squares of the error. Now those were the vertical distances y minus y hat, and so also known as the residuals. So when we take the sum of the squares of the residuals, so the sum of the squares of the errors, and we add that to the sum of the squares of the regression, we get the total variability. So the sum of the squares of the total. So just to recap, the sum of the squares of the error is the variability that is not explained or unexplained by the regression line. And then the sum of the squares of the regression line, that is the explained variability. Add those two together, you get the total sum of the squares, or the total variability. So if the correlation coefficient R is a number between -1 and +1, if we square that value, then R squared is going to be a value between 0 and 1. If we have equal to 1, let's say, so R squared equals 1, we have a perfect prediction. So perfect prediction of y by any x, and that 100% of the variability of y is accounted for by x. So the coefficient of determination is the square of the correlation coefficient. So if we look at the formulas here, here is the proportion, the SSR, in the numerator, divided by the total sum of the squares of the variability. That is what we mean by the proportion of the variability that is explained by the least squares regression line. So that is what we mean by proportion. And so the sum of the squares of the regression line can be calculated as the sum of the squares of xy from previous slides. We learned that formula, and we square it and divide it by the sum of the squares of the x's. The total variability, so the sum of the squares of the total, is the sum of y minus the average y's, so y minus the average y squared, or also known as the sum of the squares of the y's. So if we take SSE, add that to SSR, gives us the total sum of squares. And that can be handy because sometimes we know parts of that. We can, if we are trying to figure out, say, the total sum of squares, but we know the sum of the squares of the error and the sum of the squares of the regression, we can just add them up. Or maybe we're trying to figure out the sum of the squares of the error, we can use the other two to figure it out by using this formula. So using our online sales example, we can calculate R squared. So let's take a look at that. We can look at R squared. We know that the formula is the proportion of the variability that is explained by the least squares regression line. So the sum of the squares of the regression divided by the total sum of squares. And we're going to need the sum of the squares of the regression. So we need that total So we need to plug in our formula here. So SSXY, we don't forget to square it. Divide it by the sum of the squares of the x's. We can plug these in because we've already calculated these. 2326 squared divided by 4480. And we get 1207.65. So we also have calculated the total sum of squares because we calculated earlier the sum of the squares of the y's. And we got 1265. So we could check to see if this all makes sense. So the sum of the squares of the regression plus the sum of the squares of the error, which we did earlier in the last with the standard error of the estimate, we have those two values. So 1207.65 plus the error was 57, we calculated earlier, 57.555. We got 1265.2. That matches this, so it's good. All right, so we can then plug these values in. So the sum of the squares of the regression was 1207.65. Our total was 1265.2, right? The sum of the squares of the y's. And we get 0.9545. Now you might be wondering, why didn't I just take the correlation coefficient and square it? Because we know what R is. R was calculated earlier as 0.97699. And we can square that. If we already know that value, we might as well just square it. But I wanted to show it, I wanted to show it both ways. So if we square that, let's check and see if we've done all our work properly. See if we get the same. We square that value, we get 0.9545, which is good. That matches. And so it really depends on what you've been given, and based on what you've been given, you can then figure out the quantities that are being asked.